Welcome to our 2026. I am Sakib Jan, Editor-in-Chief of Deep Engineering Publication and a weekly newsletter. This is our roundtable discussion on multi-agent architectures. So over the next 30 to 40 minutes, we're going to dig deeper and actually talk about the systems that take to build and to run. It's a privilege and a pure joy to host our two guests today. We have with us today Chi Wang, creator of AutoGen and AG2, along with MassGen and also Sutando open source agentic AI projects used by NVIDIA, Google, Microsoft, and research institutions worldwide. He led agentic AI work as a senior staff research scientist at Google DeepMind, pioneered, uh, pioneered agentic AI research at Microsoft Research, and created Flammel for AutoML. He also teaches at Stanford, Berkeley, and deeplearning.ai. It is a privilege to have you over here. Thank you so much for joining us today.
Thank you. Glad to be here.
Perfect. I'm also, we also joined by Xiao Ma. He is an engineering executive with more than 15 years of experience in machine learning and AI systems. He was chief architect at Pattern Insight and at Medium. And he now leads the teams building Splunk Observability Cloud at Splunk, a Cisco company, including its enterprise multi-agent AI systems and AI observability products. Great to have you, Xiao.
Thank you for having me. Excited to be here.
Great. Before I give you guys a floor to talk, most interestingly, as I was looking at your backgrounds, both of you went to the same high school in China, same graduate school at Illinois, both working at the intersection of machine learning and systems. And now you guys are also publishing a book with us at PACT. It's about multi-agent engineering. That's very interesting, where you are expositing engineering advices on designing, building, and operating AI systems that think and act as coordinated teams. So welcome. Chi, I want to give you the floor. Please tell us something about yourself. Tell us what you're doing these days.
Sure. Yeah. Thanks all for having me here. My name is Chi Wang. I started working on agentic AI since 2023, and I created AutoGen as a multi-agent conversation framework for developers to create agents and multiple agents, connect them together to build multi-agent systems, and then later evolve into AG2. So basically, I work on several different open source projects for agentic AI, and one per year, roughly speaking. In 2023 is AutoGen, 2024 is AG2. Last year it was MassGen, and this year is Sutando. So MassGen is a multi-agent scaling system that help try to explore whether there's a universal architecture to combine multiple agents and solve very complex problems and scale them out. And this year I built a personal AI stand for myself called Stando. It started as an experiment about trying to push the boundary of if I keep growing an agent by itself, how far I can go. Can I make it do things that other agents cannot do? So that's how the experiment started, but it turned out to work incredibly well, and many other users are addicted to it too. And now we are building products, commercial products around it. Yeah, a little bit about my careers. Right now I'm working on a startup called AG2 AI that's building agent AI products. And before that, I worked at Google DeepMind as a research scientist. That's where I studied agent AI and research and pushing the open source project like MassGen. And before that, I worked at Microsoft Research, where I created AutoGen. So yeah, so it's a nice journey. Glad to be here.
Awesome. It's exciting. Thank you so much for joining us today. Xiao, I want to give you the floor. Please tell us about yourself and what you are up to these days.
Sure. I think my career is almost a journey of pain. The reason I went to Medium, Sakib, as you mentioned, is because I think the content on internet is all driven by clickbaits and advertisement. So at Medium, we try to basically build a new platform which is completely driven by the quality of content and commercialize it through subscription rather than just for advertisement. And then at Medium, I felt the pain of building microservice systems and observability. And that's why I joined the Splunk to work on, as you mentioned, the Splunk Observability Cloud. I think, well, as you mentioned earlier, I know Chi for a very, very long time. We grew up in the same hometown, and we went to the same high school, and we also met each other at graduate school. And we have a lot of common interest in the intersection of AI and systems design. That's why we we keep being a friend and also started writing a book. So that's
Yeah,
our journey.
to add that, Xiao used to teach me in the competitive programming when I was in high school. So that's how I know Xiao at the beginning.
Wow, that is very interesting, guys. Thank you so much. I want to get started. I want to ask questions first about multi-agent, just to set the stage and prepare us for the deeper discussions. So starting with you, Chi, tell us, like, multi-agent is now attached to almost everything. Now this year, what does actually multi-agent architecture actually mean to you, and is in terms being used too loosely as well?
Yeah, that's right. Exactly. The meaning of it is quite broad, I would say, and the most important paradigm can also change over time. Or when we talk about multi-agent, the specific meaning we refer to can also evolve. So back in 2023, when we talk about multi-agent, I think the reason for this change is basically the meaning of the agent and what it encompasses, what it contains, change over time. So back in 2023, at that time, the model was GPT-4, and an agent essentially is a model plus a few tool calls, and we keep making model inference using the tool, sometimes with tool calls, sometimes without, and then keep doing that inference. And so at that time, multi-agent is about how do you address the weakness of these initial powerful language models. They're already powerful, and there's also a lot of limitations. So we need to build harnesses on top of that model. So actually using how to make the model reliably using tool calls was one of the hard problems at that time. So we often need to use multi-agents to check the results of the tool call, make multi-agents perform different tasks, because a single model is hard to follow of complex instructions, and all we need to decompose a big task into smaller ones and have each agent focusing on specific problems. But the meaning has changed a lot. For example, in last year, in 2025, at that time, most of the model providers also has offered their agents with built-in tool calls, and in many cases, multiple different ways to configure the models to execute different kinds of tool calls. Search, coding are the two common ones that across different model providers. But each of them has different languages, slightly different dialects, and also have different strengths and weaknesses. And when we solve very hard problems like the last human exam benchmarks, each single model plus tool or agent at that time makes different kind of mistakes. And then at that time, multi-agent can means that we ask each agent to solve the same problem, and then we ask them to check each other's answer and try to iterate on top of that. That's MassGen project trying to mimic the study group kind of multi-agent architecture. This year, there's even more progress in, for example, personal AI, so that we can design one personal AI agent for everyone. Like you have your agent, I have my AI stand. When you use them, they interact with us and they develop unique strengths or superpower. My agent may be very good at research. Your agent may be very good at communication. And when we put them together, like make these agents interact with each other, we have even higher level of multi-agent system. Because each of the personal AI we're using maybe already contain multi-agent inside that. But on top of that, when we wrap up the multi-agent architecture inside the powerful agents, these powerful agents can still talk to each other, and we can compose even stronger multi-agent systems. So you can see there's kind of some different levels of architectures that we can combine with multi-agents, and we can do this recursively. So that's a way to understand the multi-agent architecture at different levels, and over time we may see this abstraction go higher and higher.
Awesome. Thank you so much. Appreciate for explaining that in detail. Xiao, please shed some light also on multi-agent architecture landscape, and also if you could please tell us maybe what multi-agent is not in your view.
Yeah. I think that the term may become confusing because there's a huge debate about how many agents do you really need for your task. I think at some point this has become a semantic discussion rather than the real discussion to solve problems. Because, for example, you could say multi-agent does not mean you have literally multiple repositories, multiple processes, right? Like even with one single agent, if you give that agent, different context, different memory, different roles, it can do multiple things. I think the word multi-agent here does not really mean literally you have many systems. There is a version of that, which is there's a concept of Internet of Agents. So essentially, you have very diverse agents built by different companies, built by different frameworks. They will talk to each other. That, by definition, is multi-agent. But even within your own system, you could still have the same agent play different roles, or even they play you have parallelism of multiple agents doing the same thing at the same time. You could still call it a multi-agent. So I would say not fixating on multi versus single too much, but the more think about the problem you want to solve. If you need a parallelism, you could have the same agent doing multiple things at the same time. If you need a debate, if you need agents to check each other's results, you could have multi-agent. There's one architecture for that as well. And if you need a different stage, that you have planning, you have doing the work, you have synthesizing, that's another multi-agent architecture pattern you can follow.
Thank you so much, Xiao. I also want to talk about the need for multiple agents and really about the judgment over here. So the standard advice usually is to start with one capable agent and some good tools. But tell us, Chi, when does a problem generally require multiple agents rather than one agent with more tools?
Yeah, again, this because the concept of agent evolves over time. So at different time, when we refer different meaning of agent, that answer might change. And in general, the simplest answer to that is when the problem is too complex for a single agent to handle, you need multiple agents. That's a simple way to talk about it. But if we break down that, if we be a little bit more specific, I think right now, if we talk about today's, if we refer to a single agent as, for example, personal AI agent, then I can delegate my daily tasks to it, like writing, developing code, communication, and handle just daily works. If I use that as a concept of agent, then I would say there are two questions you need to check. The first question is, can you easily provide all the context and information needed for the agent to finish the task? And the second, can the agent effectively and efficiently use all the information you provide needed for that task? These are two problems. If the answer to both is yes, then yes, a single agent is enough. If not, if either of the answers is no, then probably you need multiple agents. The example for the first question to be no is, let's say we want to coordinate to schedule meetings or coordinate to have activity together. I have my schedule, you have your schedule. Can we easily use a single agent to collect both information? It's kind of hard because we probably want to retain the information boundary. I'm comfortable of sharing my information with my agent. You're comfortable to share with yours, but we probably wouldn't be comfortable to share with common agent. And also, when during the coordination, agents sometimes need to communicate back with us, and we probably want to have some private conversation with each of our own agent. So that's example. That's a simple example of even the problem sounds like very simple, just to schedule a meeting. How hard it can be, but the answer to the first question about whether you can easily provide all the context needed by a single agent is already hard. And the second, for the second question, example is I often need to provide context in different modalities or different ways. For example, sometimes I want to just speak speak to my agent or share screen or share my camera, share vision in real time. And some other times I share information by chatting using some chat software. Although the agent can potentially combine different sources of information, but they may not a single agent may not necessarily can do all the things I want efficiently at one time. For example, sometimes I want to have some real-time result back without long waiting. And there are some certain agents that are very good at it, but not a single model plus tools. Today's technology cannot do both these different kinds of requirements. So I often need to use different agents designed for slightly different purposes, but also have a way to connect them together to solve the problem. Yeah, so these are some examples I run into in 2026. that I need to use smart filters.
Yeah, I just want to add a follow-up question over there because as you were talking, it just came to my mind. We do often talk about decomposition as well, and you probably see thousands of teams build with AG2, right? Maybe you could tell us what's the most common mistake in how people decompose a problem into agents.
Common mistakes. That's a good question. I need to think about a little bit. I think I have made some mistakes probably. I think because I'm trying to explore the frontier of agentic, I often need to try different ways. Yeah. I think in general there are two kind of mistakes, right? So the one is over-decomposing and other is under-decomposing. But I think under-decomposing is not necessarily a bad choice in the beginning, because if the problem indeed can be solved by a single agent, why should you create more, right? So you should always prefer to start from the simplest setting. And that's what I did. So you can say that's a mistake, but I wouldn't know it's a mistake if I didn't try it. Right. For example, before I started, so when I started building AutoGen, what I want is actually just build a single simple agent that can write code and iterate the code. So I write code and revise code and keep iterating in loop. So that's the initial design of AutoGen, and apparently it failed apparently, but it's still a good thing to try because it may work. For example, today with a more powerful model, I think that pattern can go very far already. So you should always keep the simple design as the initial starting point, and only decompose when you need to do it. So that's what happened with AutoGen. Initially, try to use a single agent to keep adding more instructions to handle all the errors and exceptions that I encounter during different situations, until that instruction becomes too long and the agent cannot follow. And then I just started to slowly decompose into one agent, start trying to do smaller set of things so that they can focus. But in this year, like in 2026, that kind of loop of using one agent to keep trying things and keep refining things is quite good in solving much more complex tasks than in 23 already. But then if you keep just using that single pattern for doing everything, the problem is if you will have tasks of high diversity. Some tasks take very long. Like if I want to design the agent to rewrite itself and improve itself, it's a continuous process that always need to be on. And there are other tasks that are temporary, like just writing particular specific content just one time. And if you mix these multiple types of things without good decomposition, they will hurt each other, and they will be confused about when to prioritize what. And so then you gradually add more decomposition to handle this. But always start from the simplest.
Thank you so much for that answer. You almost knocked off the question I had prepared for Xiao. But yeah, thank you. You did not go in detail talking about over decomposition. So Xiao, you have an experience working at Medium, and you also work on AI observability products. So you can actually talk about what is a signal that a team has over decomposed, that they have probably split work into agents that now only add, coordination overhead.
Yeah, I think maybe I would just build up on what just mentioned. I think I probably see more under decomposition than over decomposition, because I still feel there are in my opinion, there are three major questions we should ask ourselves when we decide like exactly how we decompose how many agents we need, right? The first one is what Chi mentioned about, can you really fit the context to a single agent? I think about this with human as well, right? Like our brain is not really good at multitasking and context switch. Like, can we really do a lot of things in one setting effectively? I don't think so. The similar thing applied to a large language model as well. The second is whether you need a parallelism. So if you really need to explore different paths to try different things at the same time for the sake of latency or efficiency, that's another reason to have multiple agents to do things in parallel. So let me give you one particular example, because we in Splunk Observability Cloud, we're tackling many different problems. We tackle how we observe multi-agent systems, but we also tackle the problem of how we use multi-agents to triage their system problems. Like all of the audience are engineers, like we all know when the system is down, we have so-called war room or a group of people coming together to triage an outage. In that setting, just think about what kind of different roles we have, right? So usually we have incident commander, and that person is really good at customer communication, really good at organizing information to post updates in different channels. And we have maybe multiple subject experts from different teams. Like someone know the service really, really well. Someone may know the infrastructure database really well. Someone may know Kubernetes really well. And they all come together. They bring different expertise. They use different tools. They can do different exploration in parallel. And then they also converge, right? Like if I have something interesting I find, I will post it in certain format. Other people can read it. And then other people may continue their triage based on what I found. And to try to like picture that kind of collaboration in a real production outage war room, and we applied that into a multi-agent system. So you have different agents to do different things. They bring their context is more focused on what they are really, really good at, so they can do a really good job very fast. And then we gather the information back, and there might be other agent to synthesize and do the next stage of triage. I think that's how, if your problem fit into that model, if you have multiple people to do the work, you need them to collaborate, coordinate, and they focus on their own expertise. I would say that's a very strong signal you need a multi-agent system. And you can think about how you decompose the task to human teams. In a similar way, you can decompose a task to machine teams agents.
Thank you so much. That is edifying explanation. Appreciate that. I want to ask about coordination and orchestration as well, particularly to Chi, because you created AG2, right? And also you created MassGen. I think AG2 grew out of a conversational multi-agent patterns, and MassGen pushes in a different direction with parallel agents converging on an answer. So tell us, how should an architect choose among conversational, hierarchical, manager, and worker, at the same time, parallel topologies? What actually decides the shape?
Yeah, it's most time is just about the problem nature that you're trying to solve, and it's often easy to tell just by thinking of like how humans can approach it. So suppose you have unlimited resources. Suppose you have you can let agent to do anything you want. What is a most effective way that from your experience about it, the problem has been solved. It's quite often just common sense. I think the non-obvious part is often about knowing what the single agent can do in your existing system. And by single agent, there are also different granularity, different levels. And so if you already have built agents of different levels, then that's good knowledge you could use, because if you start with the most powerful agent that you have built, then often the type of multi-agents will be very different from when you start from low-level agents that do simpler things. If you already have a very strong single agent that can almost solve the task, but only makes some mistakes, make some error at some times, then you could use a parallel pattern to design several diverse agents. So each of them may make different kind of mistakes, but they fundamentally can all solve the same problem, and just sometimes succeed, sometimes fail. And so that's a scenario you can apply the parallel agents and converge to refine each other's answer. And if the problem looks like very much non-solvable by the single agent, not just but sometimes have mistakes, sometimes not, but fundamentally has very low success rate, like single-digit success rate. That means you probably need to use more complex patterns that do more decomposition, so that you need to make each single agent to reach at least more than 90%, and then use some verification pattern or some independent checker agent to fill the gap of the last mile. And during that decomposition, then each agent might be doing very heterogeneous kind of things, and you probably need to use more complex conversation pattern to piece them together. So that's one way to think about it.
Interesting. And and how much coordination logic should live in explicit orchestration code, and how much should be left to the agents to negotiate themselves. If you could also tell us where is that line today, and is it moving?
Yeah, it's always moving, and the tricky part is when there are okay. So the tricky part, the most tricky scenario is when you don't own all the agents you have in the system. And if you own all of them, then you can basically profile each of them, and because you know at what level or complexity each of them is, and choose the pattern in a way I just described. But what if you don't see their internals? What if you only know I have the agent, you have the agent, and our team our team has their own agents, but we don't know how they're implemented. Or if you are dealing with some external parties agents, we have totally no clue how complex they are and what they can do. What's assumption we should make about dealing with these type of agents? So I guess when you don't have a lot of information about them, you have to make it flexible. So you probably need to design your agent to be able to deal with different type of other agents. And often you cannot make too many assumptions about how capable they are. And only if you verify what they can do, you decide to choose the most efficient way. So if you find that they're less capable, then probably when you communicate with them, you must first decompose on your side and then give them simpler tasks. Otherwise, you could just provide a very high level goal and assume they could stick to it. Yeah. So I think figuring out the profiling of the agents is quite important.
Thank you so much, Chi. Xiao, would you like to add more thoughts to that?
Yeah, I think that's I don't want to sell too hard, but that's a big topic in our book about this. But I think in reality, there are a lot of theoretical discussion we could have before we build, right? I mean, I'm not trying to trivialize the architecture design side of things, but this is also based on Chi and myself's experience. A lot of this is also coming from just trying it out. And this is where evaluation and observability really come in, right? So you could try one architecture, one topology, one pattern, and just see how these agents work together. Do they really solve your problems? And the only way to know that is you have already thought about evaluation and observability beforehand. And you need to understand how these agents are talking to each other. These are not just static code. You can just have a call stack dump and you know all the details, or you can even read the source code. But when agents communicate, a lot of the things are undeterministic during production time. And that's but once you have a really good evaluation, not just for individual LLM call response evaluation, you know the evaluation of the whole system, you know the trajectory, how agents talking to each other, what kind of information they exchange. And then you have the observability to have all the traces you can analyze. That will give you the information to really decide, do you need to pivot on the topology, or do you need a different model, or do you need to have different context setting for the agents? I think by trying different things, that's probably the best answer to really carve that line. Do you need more decomposition, or do you want more consolidation?
Thank you so much for adding to that. Also, maybe if you could, from the position of the enterprise, right, talk about, we have protocols, right? We have MCP for tools and the emerging agent-to-agent standards, right? So are we heading towards real interoperability, or just another round of framework lock-in with better branding?
Yeah, I can take that first. Well, things are evolving so fast. I think my answer may be different in just a week or so. But I think in general, on the practical view, I would say MCP and A2A are the two things that you should always start with. Many other protocols, you could consider them, but most of the production systems are not that complex. But MCP and A2A, they are all, in my opinion, they are bare minimum, right? So one, to really abstract the two use, the other one is to facilitate the communication between agents. But then if you expand to, for example, like I mentioned at the very beginning of this discussion, if you really have a so-called internet of agents, you have so many agents from different companies, different teams, I think there are a lot of other questions you should answer. And one of the framework infrastructure developed by Cisco's OutShift team agency. It tries to solve some of the problems. There are identity authorization. There are even how you run different agents, how you measure their performance. So I think that will, once your problem scope become that large, you need to worry about other protocols. But to start with, I would say have MCP, have A2A, and you can do a lot with just these two protocols.
Interesting. Chi, would you shed some light from the framework side of things?
Yeah. The framework, if we look back about the framework environment, it's indeed, so every time when the model is aggregated and when the harness on top of the model is aggregated, then that usually brings a whole new set of challenges, or basically it changes the focus point about where the interoperability is required. When the MassGen is one example. So when we start building MassGen, we don't have real interoperability across the model provider's most powerful agents offering at that time, because initially it's more about the interoperability across models. We want to have a way to delegate the same task to different models. That layer was relatively easy before last year, but so when each model provider starting to offer their own agent offering, it's not just making model inference standard. It's about their internal reasoning, their tool using, and what exposed to the developers and so on. So there's just lots of issues in that regard. So we had to build our own interoperable layer to make these agents able to not only solve the problem by itself, but also able to share and check each other's answers. So that already requires more interoperability challenge to be solved. And this year, it's the single agent's power has moved higher. And it doesn't mean the previous products are not useful. The previous products are still useful at a relatively lower level of orchestration, like how to orchestrate models and tools. You should use MCP, and how do you combine relatively simple agents talking to each other? You probably use A2A. But as the single harness becomes more and more complex, like we have the Codex, Cloud Code, these coding agents, they already have MCP building, they already have other product building, but they present themselves as even more complex agents than before. And then how do we make them interoperate with each other? Like how do we combine multiple such coding agents or customize them to do beyond coding and make them our personal AI stand that do everything, or add some non-coding type of capability like processing real-time requests, processing audio, visual. Right now, they are scattered in different type of models and different type of systems. And but what we really want is a single AI stand that can process all of these and use some unique protocols to do this kind of piecing together. And when you make the personal AI to be used by other people as well, and even let them talk to each other, like the different personal AI agents to talk to each other, then we need more higher level protocols standards. So this is constantly evolving landscape, and the previous protocols will still be useful at a certain layer, and we then need new protocols for higher layer.
Thank you so very much, Chi, for explaining that in there. I want to shift gear towards reliability and observability and ask a few questions to Xiao. Briefly, you build AI observability as a product. So what does observing in multi-agent system require that metric, logs, and traces don't already give us? So maybe you could tell us what is new or something that most people don't even know yet.
Yeah, I think we alluded to this a little bit in the previous questions. I would say, I think the biggest shift from observing multi-agent system or in general agentic systems compared to the original traditional systems is, for traditional systems, observability is more of a production system concern, less about buildings concern. It's more like operation side, right? Because you observe because you want to know latency, you want to triage outage, and usually you bring the observability data, the as you mentioned, the melt, we call the melt metrics, event, logs, and the traces. You usually use the data for triaging systems, and you occasionally use the data for engineers in building, right? Because if I know there's a performance bottleneck, if I know some bugs, I can use the data for my building. But I would say 95% of the case, it's build first and observe second. But the multi-agent system is the other way around, because the building part becomes essentially you rely on the observability data and the evaluation data for your building. One example we mentioned earlier is you don't even know the best topology, the best way to decompose your system, right? You need observability data to teach you how to do this. And then there are many cases where your building is essentially iterating on the topology and the prompt or skills, whatever the term we could use today, rather than you're just writing a bunch of code. And the way to iterate on the topology, prompt, the architecture of your agents is using the evaluation and the observability data. And the involvement even to a point where we literally talking about observability have a different personas now. So previously the personas are just SRE, it's just operation folks, right? And then sometimes the developer is also part of the persona. But today, the agent observability persona is operation folks, it's the developers, it's even PMs, the designers. There are many other functions. They need to use observability data to really build the system. I mean, some example. For example, if you are building, let's say, a customer support agent system, and how do you know? For example, if I'm not an engineer, I'm a PM on that system. I want to know if my system is responding to customer support questions properly, because I know the product requirement, I know what the system should be behaving. And then previously, I will not write code. I'm a PM. I don't know how to write code. But today, my job is literally, I will go to the observability product. I will look through some of the data set I collect from the production system. I will know if the system is answering questions in the proper way. And as a PM, I literally have a role to use the evaluation and observability product to improve my system, to build my system. So I think that's a reverse of not building first, observe second. It's everyone started building with observability and the evaluation data. That's the biggest shift I have seen.
Thank you. Thank you so much for that answer. And speaking about production systems, I think there's something important also when we talk about, which is what do the characteristic production failures modes look like actually? Things like cascading errors or agent looping or silent drift. How do you catch them before your customers would?
So I think everything you mentioned, okay, those could happen. And this is where I would add another one, which is it's a cost. Because if you read industry news, you probably already see a lot of the news about the cost. We did not really think about the cost when people first build LLM-based systems. They feel like, okay, let's solve the customer pain first. And if cost become a problem, that would be a nice problem to have. But today, it is a problem, and it's a very big problem. It's not a very nice problem to have. It's actually a very painful problem for both internal usage of AI tooling and when we build systems based on LLM and the cost one off the roof. I would say that in order to identify these problems, again, this goes back to evaluation and observability, because these are not the problem you can just design out of. You have to observe and iterate. The thing you mentioned about, okay, maybe agent, they don't converge their decisions too fast. And a lot of things you can observe from trace. So you can literally see if you have a proper instrumentation and observability product, you can literally see maybe some agents, they are just debating for too long, way too long before they converge, or there are not enough parallelism to be more effective. And we're also applying AI to identify. So we call it observability for AI and AI for observability. And these two sides of the coin are converging very, very fast, right? Once you have all these agent traces, you can apply AI to understand what are the potential problems you are seeing from these traces. Sometimes they're not converging fast enough. Sometimes they don't have the right context. Sometimes they make wrong tool calls. And once you have enough observing data, you can easily identify these anomaly with the power of AI. So I think it go back to what I mentioned earlier. I think all the things you mentioned, Sakib, those are real production pain failure mode. And the only way to identify them is you have a solid evaluation and observability system upfront. And that's not afterthought anymore. That's encoded into your building your entire development cycle.
That is excellent. And thank you for mentioning cost. I think there's a discipline that has emerged out of this. It's like DevOps or MLOps. It's called FinOps. And people are taking that seriously as well now.
Yeah. So one common type of failure I observe is a regression. The regression means so often initially we don't know when the agent can do a certain type of task very well. So we try it and we find it works, and we assume it always works. But at some time it suddenly breaks down and you have a hard time of finding out why. So that often happens when I use MassGen. And I think the reason are twofold. One is because agent by definition is we can delegate them to do many different types of things, and we don't worry about the details. So the less you worry about details, that means the type of tasks they solve will be more kind of diverse, and they need to figure out by themselves, but you cannot predict all the type of problems or difficulties they encounter. So even if they work today, it's just means for the scenarios they run into today, it works, but there can be many other situations that they couldn't handle, but you cannot know all of them in front. And the second reason is the agentic system often is a big system that contains many moving parts. The model can change. The tools underneath the model can change. The context can change. So a few working points just means that for that particular combination around that time, things work. But when things change, even when all of the things don't change, the external world might change. And because of this, there are so many moving pieces. The regression is also like harder to manage than traditional software.
I think, thank you so much, Chi, for that answer. I think it would serve us really well if we, as we are planning to do a probably event in future around when your book is about to launch, we might actually dig deeper more around this, because there is so much to talk about, things around here, and it's just like few basic questions that I just asked you guys. I think, and it's time because we also have some questions from the audience. I want to bring them on stage, and we can basically answer those questions as well. So generally, we take a minute to answer the question. So I'll just bring it on stage, and either of you can pick up the question and answer. So I'm bringing first question from Srishti, who asked, the biggest engineering challenge you face in production that most people building multi-agent systems don't anticipate. I think it's from the story side of things. Yeah, either of you can share.
Yeah, I think I've encountered many of such examples myself, and I think the regression problem I just mentioned is probably just one big thing of them. As I mentioned, the challenge is how you make the system not just work once, but always work, moving on with all the dynamic changes. It's not very hard to give it one particular task. So this is my task I want to solve. If you cannot, just keep revising until you can. So I think today's agent is quite good at that. If you give them particular task, even if it fails in the beginning, it often can figure out ways to address it. But whether the way that they address a problem is general enough that can handle all future type of tasks is not necessarily easy. So when we talk about multi-agent systems, it often means the particular decomposition of the multi-agent systems and the particular way of coordinating them need to account for all the different future situations. And I think that's still a very open problem.
Yeah, I would only add to Chi's point. I think Chi mentioned the regression. I would say even one step forward. I think the biggest question is, do you even know the first time your system works or not in real production? It probably works for demos, but does it actually work in production systems, solving real problems? I think that's something for traditional system. If you pass your test, pass your QA, pass your PSR, whatsoever, you roughly know it solves the problems because it's well defined and it's deterministic. But for multi-agent systems, to know whether it works in the first place, it's one thing which most people did not anticipate. And that's where, again, evaluation and observability come in to help.
Awesome. Thank you so much, guys, for answering that. We have another question. It's very simple. It will take just a couple of seconds to answer.
Well, I can take this one. I mean, obviously, I have a strong bias. I would recommend Splunk's Observability Cloud, which is the flagship Cisco product for observability. And I saw there's another question on the list about the Gen AI semantics. So yes, the answer to that question is certainly yes. We are a big advocate for OTel, open telemetry, for people who don't know what OTel means. It's basically an open standard to instrument and collect data for observability for both traditional systems and agentic systems. And as a matter of fact, Splunk is one of the inventors of OTel 6 years ago or 7 years ago, and we're still the biggest contributor in the open source community. And that, yes, the Gen AI semantic will be the standard.
So as most LLMs knowledge come from English, how to correct the bias? This is around bias, guys.
Chi, do you want to take this one? You'll probably have more insights on this.
So in general, one good way to correct bias is use the MassGen type of approach to not have only just one agent solving a problem, but having multiple of them. Each of them has different kind of bias. And so the more diverse you make, the chance for all of them to be wrong is smaller. So let's say, so in this particular example, it's about English bias. So if you have models that are that have really different kind of bias than the common ones, add them into the system. And another way is to not only rely on language models, but also add tools. By the way, how you configure the tools and how you configure the language models are also ways to increase the diversity. So when you configure them differently, they could behave very differently. So and then you use a MassGen type of approach to not trusting any single of them, but having the different agents join together to check each other's answer. And it's still non-trivial to find out the correct one out of many different answers, because sometimes the truth is in the minority. And if you use traditional voting, you may not necessarily get things right. So it's not simple voting. It needs to be some careful reasoning and non-simple like majority voting way to reach consensus. And often you don't just simply vote, but you think whether there's a better answer, whether none of the existing answer is good enough, whether you need to iterate based on existing answers. So when you keep asking agent to do that, sometimes that they will identify their own bias and rethink whether I should do it in a different way. So even when all the answers are wrong, but if they are wrong in different ways, and they realize they need to rethink the problem. So as long as you can trigger that, there's a hope that you can iterate and eventually get a better answer, even if you couldn't solve this problem completely.
Thank you so much, Chi. There is a lot I wanted to actually ask about. I wanted to discuss more about observability, and sadly, we don't have enough time. I wanted to also talk about governance, talk about blast radius, and a little bit more about cost. I think we would have to do another session, and I think I would aim to do that when we have our meeting next time for our session, which we will schedule in a couple of weeks, and we'll let you know, guys. And to our people in the audience, well, there's a break that would be till 12:45 ET. I know we have exceeded our time. Thank you so much for being kind to sticking around. The next session is about spec-driven development, and it would start, around 12:45 ET. So thank you so much, Chi, and thank you so much, Xiao. It's a really real privilege to have you guys here to ask you questions, and I'm really looking forward to the other session. And what we will do also is I will be publishing, a couple of articles based on our discussion today, sharing them with you guys. So I'll be in touch with you. And to our people in the audience, do subscribe to Deep Engineering newsletter, because I will be featuring both Xiao and Chi in one of our newsletter issues in coming weeks. So with that, thank you so much. We can wrap up. And yes, everyone have a good time. Chi, thank you.
Thank you very much.